SwayamPrabha. Digital India. Educated India.
Okay, so this is lecture number 19. So in this we are going to discuss about hydroforming. This is a more applied process. Probably maybe we can see it as a recent one of the recent developments in metal forming or in sheet forming or tube forming when compared to other conventional methods. So until now we have seen your cup deep drawing. And of course, before that we have seen bending and then stretching, right. So, these are the three methods we have discussed, and then we applied some simple mechanics and then derived some expressions, worked out some numerical problems, and we are at the end of this particular course. So, in that we are going to discuss about hydroforming. Again here we will try to apply some simple mechanics based discussion and then derive some expressions. Let us work out a couple of problems in this. So, as the name suggests, hydroforming basically means you are going to form a material maybe in the form of a sheet or in the form of a tube with the help of fluid pressure. Okay. Like in the previous chapter we have seen hydrostatic bulge test. Okay. This is more an applied version of that. Okay, that is what is nothing but hydroforming. So, hydroforming is a well known and established method which is used to make sheets, okay, or any tubular components using liquid pressure, okay, which can also be seen as a soft punch, you can say, which can be seen as a soft punch, one can imagine. Okay. So, there are a lot of benefits, okay. Some of them I have listed here. It includes greater drawing ratio. Suppose if you do deep drawing, we have seen limit drawing ratio, right. So, it is observed that if you do sheet hydroforming or sheet deep drawing, so one can get a greater drawing ratio, better surface quality because tool to sheet contact is minimized here, reduced spring back, okay. So, better dimensional tolerance, again the contact is pretty smooth. So, dimensions and intricate dimensions making of that is comparably better when you go for hydroforming. So, intricate shapes can be manufactured with this, okay, which can be done easily by pressurizing the fluid, and unlike in conventional stamping operations where you need a punch, okay, a tool which has the particular shape to deform the material. So, here intricate shapes can be made pretty easily when compared to other traditional methods. So, these advantages, okay, are not the only advantages we have. There are several other advantages also which one can you can get it from the existing literature, but these are the main things. More from industry aspect point of view, these are predominantly acceptable, okay. And because of this you will see that there are a lot of applications the hydroforming is having. So, not only in automotive sectors, but also in household things, like any items that we see day to day life in our households, like taps, okay, your new tubes, metallic stainless steel tubes, all these things can be made or made basically by hydroforming. So, some of the applications I have listed are basically in automotive sector, rear and front axis, engine cradles, exhaust system parts, structural body components like your sheet parts, several big sheet parts, some of the components in power transmission, they are also made by this hydroforming process. So, when we speak about hydroforming, so though we know that the deformation is given by fluid pressure, so which component you are going to make is going to determine the initial raw material required for that application, right. So, in that way we can divide this hydroforming into tube hydroforming and sheet hydroforming. So, tube hydroforming and sheet hydroforming, the principle remains same. Okay. Sheet hydroforming, you know how is it going to work. We have seen that in the previous section, that your hydrostatic bulge test is a simple example of your sheet hydroforming. That is the way it is going to work. If the raw material is in the form of tube, okay, then you apply fluid pressure inside the tube, and then you allow a tube to deform, okay, at a particular location. You will see some examples, okay, and then you make the component. So, one of the main advantages of any of these hydroforming methods is basically it avoids or it minimizes post forming operations. That is one main benefit advantage that practically people see. Okay. So, post forming operations like, for example, welding. Okay. Many times, for several applications, once you make a component, we are going to attach it or connect it with some other member, and their welding is required. In such operations can be minimized, and the entire component can be made using tube or high sheet hydroforming, okay, without any with minimized minimal post forming operations. So, other than tube hydroforming, sheet hydroforming, there are other methods also, like for example, hydro piercing is also there. So, piercing of sheets, okay, and you know that what is it, and then that can be done instead of a punch, instead of tool, one can make it with the help of fluid pressure. Okay. So, now let us quickly see some schematics of this hydroforming. So, of course, sheet hydroforming, shell hydroforming are almost the same, except that the shell hydroforming, it looks like this. The schematic, you can see that, okay, you have initial workpiece typically of some structure, okay, and then you apply this pressure P. This P is actually very important for us. Our whole discussion, mechanics discussion, is going to move around this P, okay, fluid pressure. So, if you apply pressure, so naturally these regions will try to move away, and then it will try to take the shape of the die, and you will get a workpiece like this. This is what actually we want. So, people have made a spherical shell, ellipsoidal shell, okay, and toroidal shell, okay. And then applications point of view, if you see, it is observed that water tanks, LPG tanks are made, building decorations, pressure vessel heads, large size elbow joints, and single layer, double layer materials are actually deformed to make components. These all are possible. Okay, one can refer into literature, and sheet hydroforming is a similar one. Okay, you can see the schematic. This is a simple schematic which says that, okay, this is your sheet, it is written as workpiece. So, this is nothing but your sheet is the initial raw material, and you will see that this is your die. I think you can understand this. Okay. So, this die is a closed die. So, naturally there is a shape that you have to give. A shape could be something as simple as like this, a rectangular pan or something like that, you can imagine. Okay. And between the workpiece and the die, there will be a diaphragm. Okay. This diaphragm is basically a flexible one. A flexible diaphragm is frequently applied to the sheet. Okay. So, if this is the sheet, you can people apply some sort of flexible diaphragm above that. Of course, you have to place it before deformation starts, okay, which basically separates your sheet from contacting the fluid. Okay. So, this diaphragm should not affect the plastic deformation of the sheet, as long as that is not going to happen generally. Okay. So, it is not going to disturb the component fabrication, and you will have a nicely formed rectangular pan which is given here. You can see that. Okay. So, this is your die, and you will see that your sheet has taken the shape of the die, the die shape. Okay. So, this approach has the benefit of a simple die structure, okay, and potential for cost effective production of few pieces. So, the only issue with this is it is not meant for faster production, probably by now it might have come. So, it is relatively a moderately maybe slow process, but you can make a cost effective production, but few pieces when compared to conventional forming. This is just one small thing, otherwise sheet hydroforming is very well accepted in industry. Several components are made. One can look into the photographs available in the any resources. So, tube hydroforming is, of course, is what we are going to discuss a lot in this particular chapter. Okay. These tubular components, like you can see brackets for bicycle frames or pipe fittings, I was telling you, are formed using tube hydroforming. Okay. So, the schematic is the principle is going to remain same. Okay. You can see that there is a die here, right, and so you will see that you have a mandrel type of structure, and inside that there is a tube which is kept. The tube is actually a straight circular tube initially to start with, and inside that you are going to apply fluid pressure P. Okay, you are going to apply fluid pressure P, and the black color one, this particular contour is going to tell you one intermediate shape of the tube, okay, which is deformed using with the help of fluid pressure P. So, you will see that this portion is actually can give some cushioning effect, okay, so that the tube can expand in this direction. Tube is actually deforming in this direction, okay, with some restriction, okay, and the green color portion is going to tell you the second stage, okay, the green color portion is going to tell you the second stage of tube forming. So, basically there is a tubular section to start with, and this has been converted into this type of tube. You can see that it is converted to this type of tubular structure. Okay. So, this will also give you an idea that only fluid pressure is required, or is there any other resistance required to form the tube. Okay. So, when you are forming this type of shape, okay, so which is actually shown in this diagram, when you form this type of shape, let us say. So, you are going to give, initially the tube is like this, you are going to give pressure in the tube in this way, right. So, and the material is actually going to move in this direction because of the unavailability of any restriction, okay, and then you are going to make this type of shape, let us say, and along with P, one can also give F. F is nothing but your axial force, okay. Along with P, one can also give axial force to the tube, okay, so that if the compatibility is maintained between P and F, you can have a good formed tube, okay. You can have a good formed well deformed tube, actual component can be made. This F is going to actually help the pressure, okay, to make the component free of defects. If you give large F for a particular pressure, if a compatibility is lost between the pressure and your axial force, so what can happen is you keep on giving this particular force, okay, and the P is not sufficient to push this material in this direction, then what can happen is the material will try to settle here, more material will try to settle, which can create some sort of wrinkle at this particular corner regions. So, one has to be very careful with that. But at the same time, if you do not give F or you minimize F, there are other issues that can come into it, that we will also see that. If there is no F, what is the thing? If you give F, what is the advantage? We will see that. So, in that way, if you minimize F, F is not sufficient, okay, then something else is going to happen, we will see that. But often these defects can be reduced by having some compatibility between your P and F. So, I have just given here that the tube experiences internal pressure in addition to axial force, which causes compressive stress in one direction, delays thinning and tearing of tube component. So, the advantage of giving axial force is actually you are pushing more and more material, which can help P to push more material into the die cavity. Okay. So, tube hydroforming has got similar advantages in general like sheet hydroforming. One is part consolidation, then weight reduction. So, weight reduction, how it can happen is some lightweight materials which are not formed well using conventional forming can be done in this method. So, then in that way basically you can also apply those materials for several components which could reduce the weight, and of course fuel consumption can also be reduced. So, increased part strength and stiffness, accurate dimensions, So the intricate components can be made with good dimensions, less spring back, we already seen, lower tooling costs. So initial cost could be higher, but then once it is set, then since it's going to avoid post forming operations, you can reduce the tooling cost. Okay, fewer integrated processes. These are some important advantages of tube hydroforming. Many of these are valid in general for hydroforming as well. So as I said, because of all these advantages, automotive, household, and aerospace sectors use this particular technology. Okay. So now in this particular section, we are going to see three important topics, and we are going to put some mechanics to that. First one is called free expansion of a cylinder by internal pressure. Okay. Free expansion of a cylinder, cylinder means a tube. Free expansion of a cylindrical tube, you can say, by internal pressure. Okay. Here we are going to consider without axial force. And then you apply axial force, what is going to happen? That is the second case. Third case is a separate one where you are going to convert a round tube, a cylindrical tube, into a square tube. Some important details we are going to discuss in that. Okay. So the first one, what we are going to see, number one I am putting here, is a free expansion of a cylindrical tube by internal pressure. Okay, and the schematic is shown here for you. So here you will see that, I mean, this red color one, you can say that this is actually a tube with a wall thickness of, let us say, T, and it has got a radius of, let us say, R. Okay, and internal pressure P is actually applied inside so that it can freely expand. Okay, it's going to freely expand, it's going to bulge actually, it's going to bulge equally in all the directions. So the shape is going to remain circular only, that we expect. Okay, and you want to just expand the tube. Okay, that's why we call it as a free expansion. So here I have also mentioned, as usual, our nomenclature. I have on the one direction T theta, and two direction I have T phi. Okay, T theta and T phi. And of course, we can also understand that there is a sigma theta, there is a sigma phi, and there is a sigma T or sigma 3, we can say. Correspondingly, you have epsilon theta, epsilon phi, and epsilon T or epsilon 3, any one you can keep it. Okay, these are already available for us. Of course, these two are going to be tensions. T theta and T phi is going to be your tensions on one direction and two direction. So, like in the previous chapters, here also we are going to say that the strain in the axial direction would be 0. Strain in the axial direction means along this is your axial direction, along this direction your strain is going to be 0. So, let us say your epsilon 2, that is epsilon phi, is going to be 0. Why? Because there is no constraint. Okay, nothing is actually constrained. Okay, so if you take let us say an axial length of, let us say, 1 meter tube, that will remain almost same as that of 1 meter. Okay, not much change will be there. Okay, so you can take it as let us say plane strain deformation process. So now, having said it is a plane strain deformation process, we already developed some equations which are going to use here later on. Okay, in due course we will do that. We are not going to derive it, we will simply say these are the equations that will be used. So the tube radius eventually expand while initially staying circular. Okay, that is the whole process here. So now, assuming isotropic material, naturally we know that there will be epsilon theta, right, and epsilon phi would be your beta into epsilon theta, and beta is going to be equal to 0. Why? It is a plane strain. Now you will immediately think, if beta is equal to 0, what will be my alpha? That is the way we are going to think, we will come to that. So epsilon phi is equal to beta into epsilon naught, epsilon theta, and beta is going to be 0. So epsilon phi is going to be 0. Okay, and we know that now epsilon t is going to minus of 1 plus beta into epsilon theta, which you have derived long back. This fellow is actually 0, so it is going to be minus epsilon theta, right. So sigma theta will be there, and sigma phi will be alpha into theta, sigma theta, and let us say here alpha is going to be half. Okay, we already seen alpha is going to be half, then it is sigma phi is nothing but sigma theta by 2, and sigma 3 is anyway is going to be 0. This is what we assumed right from the beginning. So I written here clearly beta is equal to 0, alpha is equal to half, you can say. Okay, so this would be your state of strain and stress. Okay, so now what I am going to do is, as usual, our aim is going to get this particular fellow P. What is the pressure equation. That is the whole idea for us here. Okay. So, if I want to know P, I need to assume some Stein-Harding law. As usual, I am keeping sigma bar is equal to K epsilon bar power n. Stein-Harding law, it is Holoman power law. I hope you understand that sigma bar is nothing but effective stress, sigma bar epsilon bar effective strain. Okay, your K is strength coefficient and n is a Stein-Harding exponent. We all know this. And when the material undergoes deformation, okay, so since it is a plane strain, mode of deformation, so what I can write is, I can write my sigma theta will be equal to 2 by square root of 3 into sigma bar, which you already developed, and of course, you have to get it from von Mises effective stress equation, and epsilon bar would be equal to 2 by square root of 3 into epsilon theta. Okay, so that would be the effective stress with the principal stress, the relationship we have here. So now let us go to this pressure equation. So the hoop tension T naught, T theta, here we have T theta now. This T theta is nothing but sigma theta into T. We already discussed about it, which is also nothing but PR. It is also nothing but PR. Sigma theta is nothing but sigma theta into T, which is nothing but your PR, where P is our fellow to be found out. And we can also write T phi is nothing but half into T theta. Okay, we wrote sigma phi is equal to half into sigma theta. So similarly, your T phi is nothing but half into T theta. Okay, so now of course, whether it will be useful for us, we will see later on. Now this P is a question for us. So P, I am going to write it as, so my P is equal to sigma theta T by R, which is nothing but 2 by square root of 3 into sigma bar into T by R, which is what is given here. This is what is given here. So P has been found out now. So only thing is, you should know the new thickness and the radius. Okay, and of course sigma bar has to be can be obtained from any flow stress model. So now hoop strain and thickness are also very important for us because this thickness is going to be in this equation. So I am just going to write sigma epsilon theta would be equal to ln of R by R naught. Yeah. So that I know that because your epsilon theta is going to be in the circumferential direction, which is nothing but connecting the radius. So ln of nu R by original R, and T, as we know that T naught exponential epsilon T, and T naught exponential epsilon T is nothing but minus epsilon theta in this particular case. Okay. So now if you put epsilon theta here, okay, ln of R by R naught, if you put, it is going to be exponential ln R, those things will be taken care, and R naught by R will come. So it is going to be T naught R naught by R, which also gives you T is equal to T naught R naught divided by R. This is also very important for us. Okay, we will use this particular relationship in later on case. Okay, so let us go back to P now. So what do you develop now? P is equal to 2 by square root of 3 will be there, that is there, and then sigma bar is my K epsilon bar power n. Okay, and epsilon bar would be connected to my already developed equation 2 by square root of 3 into epsilon theta. This epsilon theta is nothing but again connected to ln of R by R naught. Okay, so all these things will give me this equation 2 by square root of 3 into sigma bar, which is nothing but K epsilon bar. Epsilon bar is 2 by square root of 3 into ln of R by R naught power n. Okay, so and what else do I have here? T by R I have, and here I have basically T by R. This instead of T by R, I am going to write T naught R naught divided by R square. This fellow will be substituted here. Okay, so I am going to get 2 by square root of 3. In place of sigma bar, I have K epsilon bar power n, and in place of epsilon bar, I am going to have my previous equation here 2 by square root of 3 into epsilon theta. In place of epsilon theta, I have ln of R by R naught into T by R. In T by R is nothing but in place of T, I am going to put T naught R naught by R. So I am going to get T naught R naught by R square. So everything can be substituted, and I will get this particular equation. So using simple mechanics, we have got the pressure equation. So, which is nothing but P is equal to 2 by square root of 3 into K into 2 by square root of 3 ln of R by R naught power n T naught R naught by R square. What is K? Strength coefficient. R naught is the original one, R is a new one, radius, n is a strain hardening exponent, we know that, and T naught initial thickness. If you know T, you can use T, otherwise T naught R naught by R square can be obtained. So, this is a simple equation, one can get all these characteristics. Okay. So, now suppose for a strain hardening material, which is what is generally seen, n greater than 0, we know that the pressure will tend to increase as the material deforms, right. So, once you expand the tube, pressure is going to increase. So, what will happen during that time? The tube wall will thin, right. So, tube wall is expected to thin, okay, and the radius will grow. If the tubular part is allowed to expand freely, both effects will work to reduce pressure. Okay. So, on one hand, your tube wall will thin, at the same time, okay, so your radius also is going to change, which together is going to affect your change in pressure. So, that one has to keep it in mind, and at some stage, like in other process, your maximum pressure is also reached, right. So, maximum pressure is also reached. Okay. Now, if you differentiate this particular equation and put dP is equal to 0, let us say, okay, for example, maximum pressure, okay, you want to get P max. Okay. So, one way is you can take all some values for this and you can graphically plot this, you will get P max. The other way is we can put dP is equal to 0 at maximum pressure, then that maximum pressure will happen when epsilon theta is equal to n by 2, and epsilon theta would be equal to n by 2. So, similar relationship were obtained for previous other processes also. For example, epsilon u is equal to n, we said, epsilon star is equal to n by 1 plus beta, a general equation, all these things were derived. Similarly, here also, okay, the maximum pressure condition you want to put, then that can be obtained if epsilon theta. What is epsilon theta for us? Epsilon theta is nothing but ln of R by R naught, okay, R by R naught. Epsilon theta is nothing but ln of R by R naught, which is nothing but ln of your R by R naught is going to be T naught by T, maybe T naught by T, okay. So, that if you put, you will get a value n by 2. That means what? You have to keep on measuring, let us say epsilon theta, when it becomes half of the strain hardening exponent, then you can imagine that your dP is equal to 0, maximum pressure is reached, okay. After that, what will happen is the tube will swell locally, okay, there will be very localized deformation, okay, in the tube to create a new shape, okay. Next stage would be splitting occurs in the locally swelled region, okay, splitting occurs in locally swelled region, and because this is a plane strain forming, okay, splitting occurs when the hoop strain, the same fellow, your epsilon theta, okay, circumferential strain, as a value approximately equal to n. Okay. So, that means when you plot a forming limit curve, let us say this is epsilon, for example, this is epsilon theta, okay, and this is epsilon phi, you are going along this particular path to reach plane strain mode of deformation, and here your forming limit is reached in this particular free expansion of tube. Okay. So, if blue color line is a forming limit curve, then you are actually following a plane strain deformation path to reach forming limit curve, okay, and you will see that this would be your n, this would be your n, because I think we have already discussed about that. Basically epsilon star would be equal to n by 1 plus beta, if you put beta is equal to 0, so n will come. So, that is another way to, maybe you can assume that way also, one will get that type of result. So, there are two stages, one is dP is equal to 0 maximum pressure, n by 2 is going to be there, and when it reaches a forming limit curve, you will see it is going to be n. Okay. So, now the limiting case I am going to get is nothing but epsilon theta is equal to ln of R star by R naught, where R star belongs to, R star is nothing but the radius at that critical moment when maximum pressure is reached, when maximum pressure is reached. That means what? Only when R naught becomes R star, that is the maximum epsilon theta you can, otherwise you have to stop it, you cannot go beyond that. Okay. So, R can become R star, that is all. Okay. When R star is reached, you have to stop. Like for example, when epsilon theta becomes n by 2 or epsilon theta becomes n, okay, there are some instabilities, no? Reason the conditions for instability we say. Similarly, you can deform the material here up to epsilon theta is ln of R star by R naught. And when R becomes R star, then you can get P star also from this equation. It is 2 by square root of 3k, 2 by square root of 3 n R by R naught, which is nothing but your epsilon theta would be nothing but n, okay, power n T naught R naught divided by R star square. Okay. This R star, we are replacing this R by R star, ln of R by R naught is nothing but n only, and this fellow is going to become P star. This is nothing but where R star and P star are values at tube splitting. When tube splits, R becomes R star and P becomes P star, where P star is nothing but your maximum value. You have to be careful with that. Okay. And you will see the splitting occurs in that particular region where there is local swelling, and one stage before that is this particular stage. Okay. So now we have seen that we are moving along a plane strain path, okay, to reach this particular forming limit curve, which is actually a conservative window. So conservative window means your formability is limited in that particular direction. So you want to have a better forming behavior, okay. So then you need to deform this tube in a non-plane strain condition. You should not deform the material in plane strain condition, okay. The problem is you can deform it, but you need a higher n value. Okay, suppose if the n value is, let us say 0.2, okay, then as per this discussion, the material will split at when epsilon theta becomes 0.2, okay. But you cannot make a full tube from that, maybe successful forming is not done, which means you have to increase the n value of the materials. You need another material, n is equal to let us say 0.27, okay, to get a good formed tube, okay. So that is the only disadvantage you have. So in the plane strain expansion, the material fail approximately when the hoop strain reaches n. So if that is the case, normally high strain hardening material is preferred. Why? Because we are deforming in a conservative forming window. So now instead of that, so instead of this beta is equal to 0, this particular path as I mentioned here from 0 to here you reach, instead of that, okay, I can take it to beta is equal to -1. That is a constant thickness process. Okay, that is called constant thickness forming or constant thickness process. We know that beta is equal to -1, what will happen? We already discussed about it, which is nothing but an arrow mark indicating this. You are going to deform the material along this path, in which case it may not meet the forming limit curve or it may meet very late. So even you can use a lower n value to get a good tube forming. So that is why I reduce the height of this forming limit curve. Here you can see this is about let us say 0.25, here it is let us say only 0.1. Here it is only 0.1, n value of 0.1 can be used. Okay. So larger strains are possible by taking lower n value material and using a constant thickness strain path, that is beta is equal to -1. So if material is the restriction you have, then better you deform the material in beta is equal to -1, okay, by some way we will discuss it now, so that you do not reach the forming limit before the component is fabricated. If you have a higher n value material, then no problem. Okay, you can deform in plane strain mode itself and then you can make the component. So that is the advantage of deforming in constant thickness forming. When beta is equal to -1, okay, why it is constant thickness you can get, beta is equal to -1 means epsilon t is equal to minus of 1 plus beta into epsilon 1. So this we have shown here also, okay, 1 plus beta into epsilon theta, isn't it? So epsilon theta I am going to put here, and the beta is equal to -1 you put, epsilon t is nothing but 0. Okay, if you put beta is equal to -1, we already discussed it. Okay, it means your epsilon t is nothing but 0. Okay, which means thickness is going to remain same, and it follows this particular path. So let us put some mechanics to it, and in the constant thickness process, okay, the hoop and axial tensions and stresses would be equal and opposite. Correct. So when you say beta is equal to -1, your alpha is also going to be equal to -1, which means your sigma 2 by sigma 1, or in terms of this, if you say t theta divided by t phi, they are also equal and opposite, right. So alpha is equal to -1 says first, sigma theta is equal to minus sigma t phi, which is nothing but t theta is equal to minus t phi, right. And the main difference how you convert a free expansion, the case we have seen before in plane strain mode of deformation, to constant thickness forming is providing this axial force F. This is what I was telling you before. Everything remains same in the schematic except that to this tube you are going to provide some axial force on both the sides. Everything remains same. P is going to be there, R will be there, you have thickness, and T theta, T phi, everything will remain same for us. So, along with fluid pressure P, you are going to add F to it. So, F is also going to actually help P in deforming the material. So, as usual, now what we are going to do, hoop tension is given by T theta is equal to PR, and T phi is nothing but alpha into T theta, which is nothing but alpha is nothing but -1. So, -1 into PR, so it is going to minus PR. So, now this axial force F is nothing but, it is compressive in nature. So, minus 2 pi into R T phi. Okay. So, it is basically 2 pi into R T phi, and T phi is nothing but minus PR. So, 2 pi R square P will come, that will be your force. So, this much amount of force you have to give, okay, to have a successful forming. So, that is why I said that this F and P are dependent. Okay. And as usual, we can, for constant thickness forming also, we can get this relationship. Epsilon bar is nothing but 2 by square root of 3 into epsilon theta. Epsilon theta is nothing but 2 by square root of 3 into ln of R by R naught, and sigma theta is nothing but 1 by square root of 3 into sigma bar. You can get all these things from these two relationships we already have here, right. So, alpha is equal to -1 if you put -1 3 square root of 3 into sigma 1, isn't it? Square root of 3 into sigma theta will be your sigma bar, correct. So, this gives a sigma bar is equal to square root of 3 into sigma 1. No? So, sigma 1 is nothing but sigma bar divided by square root of 3. So, sigma 1 for us is sigma theta here. So, you can get, and this relationship epsilon bar relationship you can get from von Mises effective strain equation. So, now as usual we are going to assume your Holloman power law equation, and pressure, how do you get this P? P is nothing but your sigma theta into T by R, we already know this, and sigma theta is nothing but 1 by square root of 3 into sigma bar is nothing but K epsilon bar power n. So, K is there, epsilon bar is nothing but 2 by square root of 3 into ln of R by R naught power n is there, and T naught by R. Instead of T by R, we are writing T naught by R. Why? Because T and T naught are going to be same, constant thickness should be noted here. That is the only difference we have. Okay. So, let us be careful here. Of course, you can put T also here with understanding that T naught and T are one and the same here. Okay. So, there are two pressure equations, one for free expansion without axial force, which is in plane strain mode of deformation, a conservative window and forming limit. The other case is if you give axial force, so you are going to do the same operation, free expansion of tube with the help of axial force and pressure. The advantage here is you are going to be in the constant thickness forming mode, and two pressures are developed here and these two are compared here. So, tube expansion without axial force, plane strain, tube expansion with axial force, constant thickness, these are the two expressions we have derived, and you will see that the pressure is reduced for constant thickness expansion compared with the plane strain. You can find out. Okay. So, you can also derive some ratio between these two. Okay. What ratio of pressure you have in constant thickness forming with respect to your plane strain, you can find out, but it is, you can also put some numbers here and then find out that pressure in the constant thickness expansion must be smaller than the plane strain one, but you have to have the setup for axial force. So, along with the pressure internal pressure setup in the actual the hydraulic press you have, along with the internal pressure you can also have an axial force that is given. Okay, that setup also you need to have. Okay. So, axial force actually helps pressure to form the component. So, this is the second one. The first one is that, this is the second one for us. So, now let us go to the third one. Okay. So, this third one is nothing but converting a cylindrical tube into a square section, which is what is given here, the schematic. Okay. So, this is a square die, right, and there is a circular tube here of a particular thickness you can imagine, and you are giving some internal pressure to this. Internal pressure is given like this, and what do you do basically here, the material is actually going to freely expand, but of course, after some time it will locally deform, which is what is shown here. So, you can see that the tube is almost becoming a square section, and with further push, you will see that the corner region will be filled fully to make almost a square tube. Okay. So, you can imagine by conventional forming how you make it. It is not going to be so easy, but here one can do this. So, now this corner region, if you want to analyze the mechanics part of it, the corner region is actually zoomed here, and some dimensions are provided here. So, this is a situation the corner of the tube I have given. So, only just one corner is shown, situation remains same in all other corners. So, what are the things given here? You can see that R naught is the initial radius and T naught is the thickness in the contacted region. The tube is already contacting here and there is an unsupported region here, right. That is the situation now. So, the contacted region, you will see that either this region, okay, or this region you can say, okay, is nothing but you have T naught and the contact length is L, let us say. Okay, that is the initial status, and initial status also you have R is the corner radius. So, now with the, if you compare this with the next stage is given by the dotted lines, your R becomes R plus dr. Okay. That means your dr is actually a negative quantity, you are going to become a small corner. Okay. This corner, okay, is going to become a smaller corner, small corner. Okay. So, your corner radius basically decreases. So, this dr is actually a negative quantity. Okay. Anyway, so in the next stage of deformation, that is the dotted lines, you can see that your R becomes R plus dr, where dr is a negative quantity, and during that time you will see that this L becomes L plus dl. This L becomes L plus dl. L becomes L plus dl, and your T, okay, here T becomes T plus dt. T naught, T, T plus dt, 3 are there. So, T naught is in the contacted region, which is already established contact, and let us say your T is in the corner region and T plus dt would be the thickness in the corner region in the next stage, like that you can imagine. Okay. So, a portion of the tube has been enlarged so that wall touches the die at point A. So, this point is now contacted. Okay. This point is actually in touch. This is all are A points. A points are actually reached now. Assuming that the thickness is less than the radius and the contact length L is S, okay, the current contact length your L. So, this L is going to be R naught minus R, correct. So, L is nothing but your R naught minus your R, that is your L. So, the corner radius, okay, so decreases to R plus dr, that is R is a negative value during an increment in the process, while the contact length grows to L plus dl. So, when the contact length L becomes L plus dl, R becomes R plus dr, that means it is becoming a small corner, corner radius decreases. Okay. So, from this equation we can write dl is nothing but minus dr, or dr is nothing but minus dl. Okay. Dr is nothing but minus dl. So, the change in radius is nothing but change in length only, but they are opposite. Fine. So, now there is one important thing here. So, internal pressure what we are giving will force the tube against the die wall at the contact zone. So, now the contact zone is established. This L is a contact zone. Okay. This has been established now. Okay. And there is an unsupported corner region. Okay. When the material slides along the die, so you can see this a figure, you can see that. So, this is your die, okay, and as I already pointed out, so this region is already contact is established here in this portion of the your this one, and here you will see that there is an unsupported region, okay, and internal pressure P is applied, and this is your S distance, let us say. So, the material slides along the die, friction opposes the motion, okay, and tension varies throughout the tube wall. So, basically it is said that, so if you see tension, okay, T theta which is applied here, it will change with respect to the S, okay. Now, what will happen is the strain will eventually become insufficient to stretch the wall, resulting in sticking zone. So, while the tube is deforming, what will happen is in the contacted portion already you will have a sticking zone. Sticking zone means the material is already stuck to the die, and there will be a sliding zone in which further deformation can happen. That is what is given here as sliding and sticking. Okay. So, the strain is actually insufficient to stretch the wall region, and a sticking zone is getting established as shown in figure A. This is your tube. So, now the same situation I am going to put an equilibrium equation here. Okay, you will see that the equilibrium equation for an element. So, I am going to pick up an element in the sliding zone. Okay, I am going to pick up a small region in the sliding zone. Okay, and I have zoomed it in figure B, and I am going to apply some equilibrium to it to get some idea of what is the change in tension. So, I am going to say that if this is my element, and since the material is deforming in this direction, okay, so mu p is going to act in my right hand side. Okay, and since this is the die wall, and let us say the element size is ds, okay, and this is a general s distance. Okay, so ds is along s, right. So, now I have t theta acting in this direction. So, there will be some change in t theta plus del theta will be there. So, I can write t theta plus d theta will be equal to t theta plus my theta is in the same direction. So, mu p into ds into 1, mu p into ds into 1, which will give me my d theta by s, ds is equal to mu p. So, I am picking up a small element in the sliding zone, and I am going to get this particular equation. This equation says that how my t theta is going to vary with respect to s, that is along the tube wall, and that is going to be a function of mu p, and that is going to be a function of mu, which is nothing but mu p. So, this is nothing but slope. So, if you draw a graph between t theta and s, the slope is going to be mu p. Okay. So, this equation is going to give me my this particular diagram. So, tension in the unsupported corner will increase as the radius decreases, that we already know that, and as per the equation for t theta, the tension reduces linearly towards the center owing to friction, right. This particular dotted line, if you see, so this is the same diagram, the bottom. Okay. So, this is your sticking zone, and this is your sliding part, and your t phi is t theta is acting here. Okay. And with respect to this s, this is your s, and you can see that x axis is s, y axis is t theta, and you will see that your d t phi divided by ds would be equal to mu p, right. So, now what will happen now here is the tension in the tube wall is less than that necessary for yielding to right of the point where sliding stops, and there is no additional deformation in the sticking zone. So, what basically is going to tell is when you move from sliding to sticking region, because of the sticking region, okay, the deformation in the cup wall in the sticking region is going to stop, and what can happen is that can happen only in this localized region, which is a unsupported region, and you will see that there is a transition between sliding and sticking, and at that place there is a thickness Ts. Okay. So, now if you want to get this Ts, okay, if you want to get this Ts, so what are we going to do is the main thing now for us, and if we pick up sigma is equal to k epsilon bar power n, okay, since this deformation is also plane strain, this deformation is also in plane strain mode of deformation, that means you will see that perpendicular to the plane, okay, perpendicular to the plane, the deformation is not going to be there. So, you can say that is a plane strain process. For that, this is already known to us, 2 by square root of 3 into k into 2 by square root of 3 into epsilon theta power n, this is a plane strain forming. Okay. So, the tension at the critical point, that is your Ts, this particular point, if you want to get, then it can be obtained in a similar way. T theta is nothing but sigma theta into Ts, instead of T we say Ts, which is nothing but my 2 by square root of 3 k into 2 by square root of 3 ln of what is epsilon theta. Epsilon theta is nothing but T naught by Ts, okay, that we already derived, power n into my Ts will remain same. So, this T theta at that critical location can be obtained from this particular equation, provided you know what is Ts, provided you know what is Ts. Okay. And when you compare the sticking zone and sliding zone, in the sticking zone there is no sliding naturally, and the slope of the tension curve, okay, would be less than mu p. That is obvious, that we know. And if you want to evaluate pressure in the unsupported corner, then it can be obtained from the simple equation which we already derived. Okay. So, when you convert your circular tube into square tube, what we have seen is basically how tension changes when you move from sticking to sliding. Sticking zone is that zone basically where the tube is already in contact with the established contact with the die wall, and your sliding exists in the unsupported, closer to unsupported corner, and if you keep on monitoring tension, it will follow your mu p. Okay, it will follow mu p, and you will see that there is one particular transition thickness Ts, that is a critical one, okay, which can be evaluated, okay, or tension at that location can be evaluated using the simple equation, provided you know what is Ts. Fine. So, with this we will stop this particular chapter discussion. So, we have seen three important one is topics. One is a free expansion of tube without axial force, which is nothing but plane strain, mode of deformation. Next one is, to keep it more advantageous, constant thickness forming can be done by giving axial force, that is the second one. Third one is converting a round tube into a square tube, okay, which is all about filling a corner mainly, and that pressure can be obtained from this equation. But other than that, we have seen what is happening at that transition of sliding to sticking. So, let us work out two important problems which are actually theoretical in nature only. Okay, let us do it quickly. So, a circular tube with a radius r and thickness T naught, okay, which is what you have seen before, is deformed into a die with a square cross section through hydroforming. So, you need to find a relationship between R and internal pressure P when there is no friction, in the frictionless case. So, R has to be related to P, or sorry, P has to be related to R, okay, you need to get P, which is a function of R when there is no friction at the die metal interface, frictionless case. Okay. And the schematic is shown here. You can see that the red color one is the initial one R, and it has got T naught thickness, and in the next stage it is becoming a square tube with a small corner radius of R and is become T. Let us say the contact length is established L here, and here also it is L. Okay. Fine. So, now what we do is we need to get P actually. We need to get P, this fellow we need to get. So, I am just going to equate volumes in these two stages. Okay. One is the initial one, which is nothing but my R into T naught into pi by 2 times, and which is equal to my new stage, which has got actually two regions. One is a corner region, the other one is a already contacted region. Okay. So, pi by 2 into R into T, pi by 2 into R into T would be my corner one, plus I am writing T into R minus R, okay, 2 times for the two walls. You can say 2T into R minus R. These two I am going to add, okay, to equate these two. From this I can get T. From this I can get T. T is nothing but T naught divided by 4 by pi minus 4 minus pi by pi into R by R, where R is your corner radius and capital R is your the initial tube radius. So, now again let us assume plane strain. These details are already known to you. We already discussed about it. Sigma theta how is related to sigma bar, epsilon bar how is related to epsilon theta. This will give me my sigma theta, okay, as there is only one change now. So, basically we are relating T to T naught, that is all. Otherwise, the pressure equation is going to be remain same, okay, that will come back to this next in the next slide. So, sigma theta would be 2 by square root of 3 into sigma bar. The sigma bar is K epsilon bar power n, right. So, instead of this there will be, let us say, a small change here, let us say we put epsilon naught plus epsilon bar power n, for example, let us say. So, 2 by square root of 3 into K into epsilon bar plus epsilon naught plus epsilon bar is 2 by square root of 3 into epsilon theta, which is ln of r by r naught, which can be r by r naught can be written as T naught by T, ln of T naught by T. So, T naught by T, from this you can get T naught by T, right. So, that you can substitute here, okay, which is nothing but inverse of this 4 by pi minus of 1 minus pi divided by pi into r by r power n. This is my sigma theta. So, now we know what to do. We are going to pressure equation. So, P is nothing but sigma theta T by r. Okay. So, sigma theta you just substitute here, entire sigma theta value you just substitute here into T by r. You want to keep it that way, you keep it. Otherwise, you can also write T, this T again as a function of this. So, you will get this particular equation. So, this T can also be replaced with this particular equation again. So, you will get finally this is the pressure, right. So, instead of deriving a full equation for pressure in this particular section, we are working out as a problem. That is the only difference here, but here we are restricting our case to frictionless case, restricting our case to a simpler one, which is nothing but a frictionless case. We could have derived it in the previous derivation itself, but we are keeping it as a separate problem. So, it is very simple. The only thing is you need to get this T as a function of T naught. That is the only difference. Otherwise, it is a regular root with which we evaluate it. So, finally, it is addressed. So, P is related to your corner radius r in this way. You can create a pressure versus r, a graph. Let us go to next one. Next one is also an application of what we discussed in the Q1, problem number 1. So, there is a steel tube of 180 mm diameter and thickness of, let us say, 4 mm, okay, that has to be expanded by internal pressure to a square section. So, okay. So, a circular one should be converted into a square tube, but there is one constraint that the maximum pressure available with the person is 64 MPa, okay, or the machine has got a limit of 64 MPa only, okay. That is the maximum pressure you can have. Within that, you have to make this particular tube. So, the material has got a stress strain behavior with a K in MPa, 700 MPa, epsilon bar power 0.2, n is given, K is also given. So, now what you need to do is you need to get the minimum corner radius. Basically you need to get r, that can be achieved under frictionless case, which is easy for us to understand. So, determine the minimum corner radius. Okay. So, now we need to understand one important thing, this minimum corner radius, that is r star, we said, no, something like that you can imagine. Minimum corner radius means that is a critical limit we have. Okay. Let us say this is going to be your r star, which we have seen in the previous derivation, right. So, this r star has to be reached means this can be reached either because the tube is necked or maximum pressure is reached. Okay. So, either it has to reach necking, either it has to reach a forming limit curve, okay, or it has to reach dP is equal to 0. Let us say maximum fluid pressure is reached. Okay. So, now depending on our availability of data, we will do something, but before that let us list out what all the things we know. This equation is known to us, just now we derived it for a frictionless case, and we also know this, isn't it, for a plane strain process, epsilon theta is equal to minus epsilon t, which is nothing but ln of T naught by T, which is also nothing but r by r naught. Fine, let us keep it like this. So, now what we are going to say is for local necking of tube wall, okay, I am going to say that is epsilon theta would be equal to my n value, which is nothing but 0.2, correct. That is why we got one previous equation, okay, you can go back and check this particular equation, the free expansion. You can see that this P star is obtained by that condition only, epsilon theta is equal to n. So, now what we do is if you put this epsilon theta is equal to 0.2 here, so 0.2 would be equal to ln of your 4 by t, let us say, okay, and from this you can get t, of course t would be less than 4, okay. So, t would be less than 4 mm, which I got it as 3.27 mm. I got it as 3.27 mm. So, this is the thickness limit we have, 3.27 mm. Okay. So, now we are going to somehow bring in the 64 MPa, right. you have to bring in somehow 65 MPa. So, pressure equation also should be used. This pressure equation was derived just in the previous slide only. I have just written here for our convenience. Now, here what we are going to do is we are going to do some iterations and we have to do that calculation and get the answer. So, now here what we are going to do is, as we know that R is going to change with P will also change, you can draw a graph between P and R, right, something like that you can imagine. So, I am going this equation, I am going to change R values from, let us say 40 to 30 mm, okay, 40 to 30 mm, and I am going to find T, sigma theta and P using all known equations. Okay. My T can be obtained using this equation, okay. R also can be obtained, okay. T can be obtained and sigma theta can be obtained, my previous derivation which I already said, the equations are there, and P is this equation, okay. This also here we can obtain it. If we can obtain P directly, that was also fine with the help of T. So, now you may take maybe 10 different values, 40, 39, 38, 37, 36, 35, 34, 32, 31, 30, like that. If you can pick up 10 different values after this 10 iterations, okay, you will see that when R is equal to 31, when R equals to 31, you reach a pressure of 63.5 MPa as per this particular formula. As per this particular formula, you can just work it out, okay. One after another you can put, okay. So, R, then you can put T, then sigma theta and P. So, here you can say 10 different values you can see, find T, sigma theta and P. You will see that when R is equal to 31 mm, you will see P is going to be about 65.5 MPa, 0.5 MPa, which is actually the limit of the machine, which is set as 64 MPa. Okay. Then one can say that hence a minimum corner radius is 31 mm, okay, and is limited by maximum pressure, and is limited by the maximum pressure, which is nothing but 64 MPa, 64 or 65, 64 only, 64 MPa. So, 31 is the minimum corner radius. So, the question is what is the minimum corner radius that can be achieved under frictionless case, okay. Because it is a frictionless case, this formula we have chosen. If it is with friction, then we do not know, your model could be, equation could be different, okay. If this is the frictionless case, then this is the formula you have to choose, okay, and you can get different values of R values you can substitute and you can get maximum pressure, and where it is going to cross 64 you need to see at 31 mm it will be closer to 64. So, you can say 31 mm as a minimum corner radius, right. So, let us stop here, we will discuss the further parts in the next session.